Good afternoon, everyone, and welcome to Chase Plastics Chase the Knowledge webinar on polymer, mechanical, and chemical testing. My name is Sherry Cudd, and I am the Advertising and Marketing Manager here at Chase Plastics. Thank you all for your interest in attending this webinar and for taking time out of your day to attend. We have a few quick housekeeping items before we begin. Everyone except the presenter is on mute and will be for the duration of the webinar, but if you'd like to ask a question, you can do so at any time by typing it in the questions section of your toolbar. If you'd rather ask your question verbally, please raise your hand using the react icon on your toolbar, and I will unmute you and call on you to ask your question out loud. If your question does not get answered right away, we will address it at the end of the webinar. You can access and download PDF copies of this presentation, our product line card, and information on our technical engineering team in the materials section during the presentation. If you are attending live, a certificate of completion and recording of the webinar will be emailed to you about an hour after the webinar concludes. You will receive a separate email from Andrea with a PDF of her presentation and handouts. We would greatly appreciate it if you could complete the survey at the end so we can improve future webinars for you and cover the topics that interest you most. We encourage you to check out past webinars and recordings on the webinars page of our website at chaseplastics.com/webinars. If you would like a custom Chase the Knowledge presentation given to your organization discussing a specific topic or material, please send an email to your presenter, Andrea Kendrick, or myself. Our entire sales team and technical team are always ready to assist with technical issues, material selection, and educating you and your team on products and processes specific to your needs. Future Chase the Knowledge webinar announcements will also appear on this page as they are posted, including an upcoming 5-part series called Chase Plastics 101, where we will discuss polymer basics, modification, testing, fabrication, and common polymers. The dates are to be announced, but will likely run each month from May to September. You can now subscribe or invite coworkers to subscribe to receive notifications of all future Chase the Knowledge webinars by clicking the subscribe here for webinar notifications button. Another great technical resource is the Chase the Knowledge blogs on our website. They can be found at chaseplastics.com/blogs or under the resources tab from the homepage. In addition to our presenter, Andrea Kendrick, who I will introduce in a moment, we also have Jason Merkel, Technical Manager, on hand to answer your questions today. At this point, I'd like to hand it over to our presenter, Andrea Kendrick. Andrea is a technical training engineer with Chase Plastics and has been with us since 2015. She received her bachelor's degree in plastics engineering technology from Ferris State University. For those of you who have attended Chase the Knowledge webinars in the past or contacted our technical engineering team for assistance, you're very familiar with Andrea and the level of expertise she brings to the table. Without further ado, Andrea.
Hey, good afternoon. It is Andrea Kendrick. Today we're going to go over polymer mechanical and chemical testing. So our agenda for today, we're going to talk about failure analysis. All of this testing that we'll be discussing will have to do with tests that are more geared towards failure analysis. We'll talk about material and part analysis. We'll go over some of the specific tests that are used for that. So we'll go over identification tests, FTIR, DSC, etc. We'll go over some property tests, so GPC, MFR, some others there. And then finally, we'll talk about part performance and then potentially the connecting tests we might do if we're having certain issues, we're seeing certain issues, and then also material identification. And so again, when we kind of go through these tests, just know that it's geared more towards failure analysis and material ID. There are some additional tests that I will not be going over that you likely use all the time or maybe have heard of. Stuff like DMA, I will not be discussing, stress strain curve information, things of that nature, because it's not necessarily geared towards failure analysis when we're talking about those tests. So, but they're out there, and if you want additional information on it, please feel free to let me know and we can certainly get that for you. All right, so failure analysis. It is the use of different techniques and tests to determine the reason for a part failure. So you have a part, it's exposed to something, it's doing something, it's coming out of the mold, whatever it may be, and it fails. And so some of those types of failures might look like a fracture, stress cracking. If it's fatigue, maybe in use application, it goes through fatigue. Discoloration, maybe in the pellet form or in the part form after it's been molded. Distortion, contamination, just to name a few. Some of them, hopefully, maybe we're catching before it gets to the part itself, but all potential issues that could result in a failure of your part. So when we use these different tests, a lot of times we'll use multiple tests in conjunction to start to paint a picture to understand why the part failed. Sometimes, again, it's easy enough if it's caught before it's apart and it's pellet contamination and there's stuff in the box or the bag. Easy enough. We're not going to mold that. We're going to get some material that's not contaminated. Sometimes it's a little more difficult to understand. Maybe the part is black and so there's hidden splay. Maybe there's voids. Maybe there's something that could cause the part to not work correctly. And so we're going to go through some of the ways that we would look into that and utilize certain chemical and physical tests to determine what might be an issue. Some things to note here when we're talking about part failure that we're going to want to consider. Stuff like, is it present initially? So when I first made the part, when it first came out of the mold, and maybe we put it in application testing, or maybe right out of the mold, was the problem showing up right then and there, not further down the line? It could be a possibility that maybe just in that case, the wrong material was selected for that application. Maybe we didn't know that it was going to see certain exposures or something that would cause a problem. And so maybe we just picked the wrong material and we got to go back to the drawing board and select the right one. Or it could be issues with processing. So maybe we selected the right material, it's going to do what it needs to, but maybe it wasn't processed right. And so you get an initial issue, molded in stress, something happened to the part when we processed it and it was a problem. Or a design that might be restrictive. Maybe the gate is a little too small. Maybe there's not adequate venting. There could be something that was designed in that's causing issues with the material. Or is it something that was not present initially? We made a bunch of good parts, or we've been making this part for years and we've not had an issue. Now we're having an issue. And so we got to figure out, was it that the right material was there, but maybe there was a processing change? Did it go to a new molder and they processed it slightly different? Or was that particular lot of material a problem? And so we would use some of these tests to maybe determine that. Or if there's a new chemical, thermal, or UV exposure, to name a few, that the part is seeing now that wasn't an initial requirement for when it was originally made. Maybe this part was meant to be used here in Michigan where I'm at and not used in Arizona or Florida, where you're going to see a lot more UV, and in the case of Florida, more humidity. And so maybe that wasn't initially a determining factor in what material we would use. So that could be an issue. Okay. So now the whole process really condensed down for failure analysis is going to look something like our part history. So starting with that, a lot of the questions I just asked on the previous slide, is this an initial problem? Is this a new problem, but you've been making it for a while? Are there new processing procedures that are being used? Is this being used in a new environment? Whatever it may be, we want to get the full history to really determine, okay, are we narrowing it down to maybe this material lot is the problem? Are we narrowing it down to the material being selected was the problem? Whatever it may be, we want to get the history first so we can start to diagnose the problem itself. The next thing you're going to do is a visual examination. And so you're going to take your part and you're going to see, what is the actual problem? Did it break? Did it snap? Is it the wrong color? Does it have a burn on it? Whatever it may be, we're going to look at it first. And there are some additional tests that I do not go over, but to look at it at a little bit more of a microscopic level. I don't go through those tests specifically, but generally speaking, as a molder, you're going to look at it first. You're going to see the problem. Hopefully, you'll see the problem and then it doesn't go into application, right? But you'll look at it first and see if you can find the issue. Then you're going to get into the part and material analysis. And so this one's in bold because these are going to be the tests that I go over specifically to really analyze what could be going on for the material. And then lastly, you're going to determine the failure mode. So by doing these different tests, painting this picture, are we able to figure out where we think the issue is stemming from? Processing, design, that material lot, whatever it may be. And then lastly, as the final step in failure analysis, hopefully, is that we correct the issue and we don't continue to have a problem. We fix or get a different lot of material, we fix the processing, whatever it may be. Ideally, that's the end result. We fix whatever issue we're having. So, but the purpose of this particular presentation is to go over the material and part analysis. So with that, some of the tests that we're going to go over in a little more detail. Not enough where I'm going to help you read a curve necessarily for any of these, but enough that when you hear these acronyms, you're able to understand kind of what they're looking at and the result of those tests and what you're going to see from them. So we're going to go through all of these different tests and there'll be different graphs and different pictures to show you kind of what that looks like. And so similar to the ones you can see over on the left-hand side, top one being an FTIR and the bottom one being a DSC. There'll be more curves on those pages as well, but we'll go through that. And then we'll talk again about part failure a little bit and then part identification as well, material identification utilizing these tests. Okay, so Fourier transform infrared spectroscopy, FTIR. You'll notice a lot of these have really long and slightly complicated names. So moving forward, I'll give you the name and then I'm going to use the acronym. It's a little bit easier. And so for FTIR, these are kind of what the machines are going to look like. And so generally speaking, all these that you're going to see, they're kind of small. I wouldn't call them large machines by any means. You can put them on a desktop. It also goes to show that for most of these, really small sample sizes are needed, about a quarter in size for this particular test. So it's not something that requires an entire huge part, whatever you're making. We don't need the entirety of it to do FTIR on the part. We would just need a small little sample. Or if you make a small part, then we use that part, right? So, but to show small equipment, a bunch of different, manufacturers of this type of equipment, but all small. Okay, so FTIR, what is it specifically? It uses infrared energy to create vibrations within the polymer's molecular bonds. And so it vibrates it. Those vibrations then reveal the structure of the polymer. It starts to create a fingerprint, if you will, of the material. So all of the different bonds within a material are going to show on your IR spectrum, which is kind of the picture you see to the right. That's your infrared spectrum of nylon. So within a nylon chemistry, you would have stuff like your NH bonds for your amine groups. You'd have your C double bond O's for acids. And so those would be present in your FTIR. And so it gives you a fingerprint of what that material looks like. So having those NH bonds and C double bond O bonds are going to be different than, say, if you were to look at a polyethylene. That's not going to have those bonds or those elements within it. And so it's going to show, and they're all unique for the material. The one thing to keep in mind here is that it's a great test for material identification. So as mentioned, it gives you where the different bonds are and the different elements then that would make it up because of the stretching or the absorbing of that frequency. But it does not help you to distinguish between materials with similar chemistries. So nylon, as the example given to the right, is going to have, again, those NH amine bonds, those acid bonds, and your CH bonds. And so all of the different linear nylons that we're talking about are going to have that. So a nylon 6 versus a 6,6 having the same bonds is going to look the same on FTIR. And so we can say it's nylon for sure. We cannot tell you at this point, using only FTIR, that it is a 6 a 6,6, a 4,6, whatever it may be. So, but great to get a first start of this is the material family that this material is. Okay, so again, great for did we use the correct material? So if you've got a part that's breaking, you've got material that's clogging a gate, you've got material that appears to be contamination within a bag or box of material, FTIR can be used to determine what it is. So if you've got or purchased nylon 6 and they do an FTIR curve and you're showing the spectrum of acetal, well, that's your contamination. Somehow some acetal material got in with your nylon, and that is a problem. So, and with other parts too, not just the material being a contaminant, but others as well. So contamination accidentally ending up in there, we would be able to tell that. Another thing that you can tell from FTIR is when bond formation starts to occur because you have oxidation or hydrolysis. They will also show on the IR spectrum. So when you have some degradation, you'll start to see that. And actually, when we go through some of the testing further in the presentation, I have that degradation shown in an FTIR curve for ABS that was exposed to UV. And so we'll get to that. But if it's degraded enough, you'll see a different part of the spectrum showing up on the FTIR curve. The other thing that you'll note too is the two examples that I gave currently, they're done by percent transmission. That's why you have the percent T. Sometimes, or if you get them from other places, you'll see it's done by absorbance versus transmission. And so if it's 100% or near 100% transmission, nothing's being absorbed by the polymer. It's going right through it. And then on the sections where you see the peaks, down on this particular one, you can see them at 3,000, a really big one at, we'll call it 800 for the acetal. That's not very transparent in that area because the acetal is absorbing it because of those bonds. And so when you see a different FTIR curve done by absorbance, it would just be the flip. So it'd be the mirror image of it. And so the peaks would go up versus down. So I just wanted to point that out because sometimes you'll see it shown like that. And I just want to put it out there that they're showing you the same thing, just transmission versus absorbance by the polymer. So keep that in mind. Okay. All right, so FTIR, material identification. I know it's nylon, perfect. Now we'll move on to differential scanning calorimetry, so DSC, and some of the machines used for that. Again, you can see they're pretty small. And so this is desktop stuff. You wouldn't know that all this cool, crazy analytical stuff is going on in it necessarily, but just a small little guy sits in your lab on a table and does some cool analyzing for us. So DSC, it's using heat flow, or heat flow is measured, and it gives us information regarding the exothermic and endothermic reactions within a polymer. So the exothermic, meaning give off heat, and the endothermic, meaning it takes in or requires heat for the reaction, it shows our thermal transitions within the material. So when we talk about glass transition temperature in both your amorphous and semicrystalline materials, being when the molecules can start to move a little bit, it shows that as a peak. Then you have your melt temperature for semicrystalline materials, so TM. And so when the crystals are able to start breaking apart, that'll show as an endothermic reaction, and you'll see a peak for that. And then crystallization temperature, if you run it through a second one, it'll show your recrystallization temperature, T sub C. So as you're cooling it off, when it will start to crystallize. So a great use of this would be after we've done FTIR, we know that it's nylon. We can turn around and do a DSC to determine what nylon it is based on its TG or TM, depending on which part of you do. Most of the time you use the TM for it. But knowing that a 4,6, a 6,6, a 6, a nylon 12 are all going to have different melting temperatures, we're able to then go, FTIR told me it was nylon, DSC now tells me what type of nylon. And so what you'll see over here in this curve is you'll see the endothermic reaction down here. It is taking in the heat to melt. And so this is for a nylon 6,6. You're showing the reaction on this particular one at 262 degrees Celsius. And so we know the TM of nylon 6,6 is right around 260, 265. So that would be right in line with what we would expect it to be and what it is showing us on the curve itself. The other thing that it can show us, which is helpful if we're getting really deep into figuring out part failure analysis, is for our semi-crystalline materials, because we can run it a second time, we can compare the level of crystallinity achieved during process, so your first run, after there's a slow cooling process, and it will allow us to know how much is the optimum crystallinity and if we are achieving that. So in that regard, if you're running a semi-crystalline material, a PET, a PBT, a nylon, and you're processing it with a mold that's too cold, we're not allowing it to crystallize to the full optimal amount. And so we basically rush through its cooling cycle. We don't allow it to crystallize adequately. We're going to have issues with stuff like our wear performance or our heat performance, chemical resistance performance. And so if we're having a material or a part that's failing with something like that, that under circumstances you would think would be reasonable to expect that material to perform like that, we could do a DSC to determine if we're meeting the optimal amount of crystallinity we should be, or if we're going through it too quickly and not allowing it to crystallize fully. So it is a good test to be able to do that. The other thing that it can show, if you know where to look or you know those particular thermal transition points for those materials, if you're starting to degrade the material, whether it be during processing or wherever it had occurred, what you're going to find is when you do the DSC, you're going to see a lower TM, a lower TC for your semi-crystalline materials. So if we were to go back to the nylon one where it had that peak down at 260, it would be a lower value. So maybe it would start in the 240s, 250s. And so it's a lowered value. And then for amorphous, similar, but with the TG value. And so you would see that it would be lowered because it's not, it's being degraded. And then part of it, if you're looking at it, and a lot of different materials have a lot of different, the graphs are a little different, but overall you'll see an initial dip, which is going to be your glass transition. This particular graph is for PET, so it is a crystalline polymer. You can see it has a crystallization peak. So you have your initial dip for glass transition of this one. Then you have an exothermic reaction, which is your TC here. And then again, the melting one, which is going to be your endothermic. You'll have to check. Sometimes they will flip these charts as well. You'll have to pay attention to the flow. So if it's going into the negatives or lower values, it's taking in heat. And so the polymer is taking in heat. It's going through an endothermic reaction. If it's a higher value, it's giving off heat. And so an exothermic reaction. Sometimes they'll flip it. So the melting will be a peak upwards versus down. So just pay attention to the axes to see which one it's showing you. But a great way to determine these different thermal transitions for our materials. Okay. Thermal gravimetric analysis, TGA. And so again, we're not really getting any bigger. The machines are still really nice and small, sitting on your desk, able to do these. But smaller does not mean that it costs less. These are expensive pieces of equipment. So we keep that in mind as we're talking about them, right? So TGA is going to be a measure of change in the sample. It's weight change based on rising temperature. So different parts within the polymer's formulation is going to decompose or become volatile, give off at different temperatures. So we start at, room temperature, lower temperature, and we raise the temperature up. And as it's being raised, different parts of it are going to burn off or decompose, and it keeps track of those changes in weights as it's going. And so this is a great, if it's available, mind you, this is an expensive piece of equipment. Not every supplier or lab necessarily will have this, but if they do and they're able to use it, it can be great to be used in conjunction with FTIR to determine the amount of constituent parts within the polymer formula. And so your FTIR, again, just tells you what's in it. It doesn't tell you how much. And so if we've noted that maybe it's a PCABS that's in there, your TGA would be able to maybe tell you, here's where your ABS is burning off, the PC portion. If it's a filled material, you'd be able to tell whatever's left over. So the last bullet, remaining weight at the end, is typically attributed to inorganic fillers. So stuff like your glass would be left afterwards. So you'd be able to tell how much of each is in there and then how much of your glass is in there. It also can typically get to a little bit lower levels of telling what's in there than some of the other methods. So if it's something like the FTIR, generally it's kind of accepted. If you're under 1% of something, it's not going to show up. You have the potential of being able to see it with the TGA that you are not able to with the FTIR. So a great way to distinguish what's in it, and now tell me how much of it is in it. And so what's available for that. Okay. So a lot of places, instead of using the TGA for reinforcing agents like glass, again, inorganic, a lot of times ash content testing is done instead. So TGA is a lot more sophisticated. If we're doing something, a production run or something for a quick comparison or figuring out what's in it, ash content is a great option for something like that. Essentially, for ash content testing, you take your organic polymer, so ABS, and it's filled with glass, and it burns off the ABS in the oven, and it only leaves the glass remaining. And so they're able to measure that and give you an idea of how much glass is in the material. So when we say it's a 30 glass filled nylon, 40 glass filled nylon, whatever it may be, generally then what you should be seeing on a cert, so certification of analysis, so this is all the tests done on that particular lot of material that was made, ash content should be on there for your filled grades. And so if it's glass filled, you're generally going to see ash, which is what I've highlighted in the little snip of a cert that we get for some of our filled nylon. You can see that this is a 33 to 37, so nominally a 35% glass filled grade. This particular lot of material that was sent to us and we sold to our customers came in at 35.31% glass. And so a quicker, not as complex or complicated way of doing it would be to do an ash content test for glass. So that's done pretty frequently as well. Okay. Thermomechanical analysis, TMA. And so this is a thermal analysis that's going to compare dimensional or volumetric change as a function of temperature, force, or time. Generally, it's per temperature because they use this test most commonly to determine your coefficient of thermal expansion, so CTE of your materials. What's nice about it is not only will you determine that across the range, but you can also use it to determine then your transition points. So similar to the DSC being able to tell you your thermal transition points in the material, a TMA will do the same thing. A TG of a semi-crystalline material is going to show you a sudden increase of your CTE. And so if you look here on the graph, you can see it's kind of gradually there, and then it kind of takes a steeper turn. This is going to be your glass transition temperature of a semi-crystalline material. And then your TG of an amorphous material, because it's more of a gradual softening, as you'll hear us describe it quite often. Generally what happens with your amorphous material, because it gradually softens, it'll actually show a little bit of a compression in your CTE. So you'll see a little bit of a drop. So this particular curve is not for amorphous, it's for semi-crystalline. So we can use that to determine those thermal transition points as well. It's also the other reason, if you've dealt with it much or you've done much with it, when you ask us, and then in turn, we ask our suppliers of the material that they make, if you're asking us for the CTE or CLTE, we generally want a range because as you can see, it changes based on the thermal transition of that material. So we want you to tell us what range you're looking for that information within. And that's where we can go and find that on average, the change. TMA can also be used to determine molded in stress, specifically in your amorphous materials. So instead of showing that compression after the TG, it'll actually show an increase in your CTE right nearing your TG. And so as you know the TG of, if we're using the ABS as the example again, as it's nearing the TG of that, you're going to see a spike versus a drop off that you would expect because of the ABS material. The other thing that it can be used for, which is unique, not necessarily for failure analysis, but if you've seen data for chemical resistance that deal with volume swell, I see it more commonly with soft touch materials. So if you see like TBV materials that are exposed to different oils, ASTM oils and gases, it gives you a dimensional swell as a percentage versus time, um, and sometimes also with temperature as well. But this can be used to do something like that. So a unique way of getting a few different bits of information out of this test. And so great test for stuff like that. Okay. All right, a quick little break in all the different tests to talk about molecular weight briefly. I don't know if I've talked about it specifically in any of my presentations to the extent where I had a whole slide for it, but it is important for the next couple slides that I talk about it. So molecular weight, MW, is defined as the weight of the sample divided by the number of moles. And so the equation is given M equals W divided by N. And so if we were to put it real simply, it has to do with the length of the polymer chains is kind of what we use it to determine. So how long are my chains of the material? And so differences in your molecular weight, a higher molecular weight, so longer chains, is going to result in more chain entanglement. So they're going to get tangled within each other. It then allows for better melt strength. So if you hear us say higher molecular weight or lower flow, you're going to see generally a better melt strength. That's why if anyone listening is in the extrusion game, you want a low flow material. It needs to have the good melt strength, and it needs to have that chain entanglement to really hold it together as it's being extruded. And so molecular weight plays into that. The other thing to be noted here would be same polymer type can have vastly different performances or very large performance differences depending on its molecular weight. So an example of that would be your polyethylene. So you think of, your high density, your low density, just very commodity based, great for a lot of different things, but we wouldn't consider it an engineering polymer by any means. Versus your ultra high molecular weight polyethylene used for very high abrasive wear type applications. For a while, they're used for, the non-ice skating stuff. So quite a difference from the polyethylene that you would see used as, more of like a tote or something like that. Vastly different, all because of our differences in molecular weight. And then to note that, then a change within the same material or even the same lot or whatever it may be, if you see a decrease in the molecular weight, so we'll get into a couple of ways to test that, but if you see a decrease in molecular weight, generally what's happening is there's degradation that's occurring. It's going through hydrolysis. So there's moisture within the material when you run it, and it's breaking up the chains, making them shorter, making the molecular weight lower, or it's oxidizing. And so you're going to see a decrease in molecular weight for that. Or in some cases, if certain degradation will result in the material starting to cross-link. And so cross-linking then is going to increase our molecular weight. So if we suspect that there's degradation of some sort, we can look to the molecular weight and do some testing on that to see if it gives us any idea of, yes, in fact, we did lower it or increase it and what that might mean to us. So with that, gel permeation chromatography, GPC, it is a quite complex process. It's sometimes also referred to as size exclusion chromatography, if you've heard it that way. But essentially it uses different columns, one or multiple, depending on how sophisticated it's getting, to segregate the different constituents of the polymer. So in the case of maybe it's using more lower molecular weight type stuff and it's got additives and stuff, pull it apart from the base polymer. And then we continue to segregate it even further by molecular weight. So being able to do that allows us to get an average molecular weight of the polymer. It's representative of all of it because within the separation of the molecular weight, we can get the distribution as well. And so overall, though, it gives us the average molecular weight of that polymer. So in the case where we're suspecting there might be degradation, so a lowering or an increasing of molecular weight, we can take the control, maybe pellets or a good part, and then compare it to one that we suspect there's been degradation, and compare the molecular weight. If the molecular weight lowered, maybe there was some hydrolysis or oxidation that occurred. If it increased, maybe there's some cross-linking. And so we can use GPC to look at that. On the flip side, the more common way to do it, only because GPC is quite expensive and it's a very complicated process. It's also kind of complicated to try to interpret the results. And so you'd have to have someone that's quite trained to be able to do that. A more simple way to do it would be to do a melt flow rate comparison. So in the materials where you can use melt flow rate, there are some that it is difficult to do that with, stuff like your nylon or your polyesters, because they're heavily influenced by moisture. We would not use necessarily a melt flow rate for it. But melt flow rate is a good indication because it is inversely proportionate to the molecular weight. So if you have a higher molecular weight material, you've got more entanglement that's happening, you're going to have a lower flowing material, so lower melt flow, and vice versa. So if you've got a lower molecular weight, it's going to have a higher flow. So if we suspect degradation has happened, we can take the melt flow of the control and compare it to the part and see if there's been a change, an increase maybe for hydrolysis, decrease maybe for cross-linking, and we can compare that. Melt flow is also a much more common test. As you might see, they are commonly found on data sheets, so we have a general idea of where it should be. So in the case of our CP prime A188 ABS, it has a melt flow of 5.6. If suddenly it decreases or increases based on the molecular weight, so if we degrade it greatly and the molecular weight decreases, our flow would greatly increase. So if we were to test it and somehow we tested at 15 or 20 melt, we've severely degraded that material because we're breaking it up. It's flowing so much easier now because we have messed with the molecular weight. And so could be a way to test that as well. In some situations, we could do viscosity in a different way. And so, as I mentioned, the nylons, the polyesters that are affected by moisture, we can't really use melt flow. We could do viscosity testing. And so we could do that different. Melt flow just tends to be the most common, so that's what I mentioned. But there are other ways around it if we don't have the option to use GPC, which, if we're being frank, not a ton of our suppliers have that availability to them. Some of our more sophisticated ones definitely will, but it's not, I wouldn't call it a common piece of equipment for sure. Okay. All right, so we talked about the different tests to kind of do part analysis. Again, there are other tests that I didn't go through and mention for part material performance. Those are used more on maybe the engineering side up front to determine the right material, not necessarily once we're having issues. But all this to say, our part performance itself, so once we're making parts or we're getting ready to make parts or we're making parts and now we're having issues, the overall performance of our part is going to be dictated really by these four main things. There's some other probably smaller things, but these four things are really the big ones at play for it. So part performance is going to be heavily dictated by the material. We got to make sure we select the right material for what it's going to see. The next one would be the design. Did we make a corner a little too sharp? Now it's going to break there or shatter there. Did we make the walls a little too thin, a little too thick? Did we not design the gate large enough for it? Whatever it may be. If we're not designing it well, it's not going to perform well, even if we've picked the right material for that application. Then you have processing. So if we've picked the right material, we designed it perfectly, everything's great. If you don't process it correctly at the right temperatures, at the right speeds, whatever it may be, you still can cause the part performance to suffer. And then lastly, your environment. So you could pick the right material, you could have the perfect design, you could process it great, but if it's in an environment that we didn't necessarily or weren't aware of or didn't know that we had to pick a material to withstand all that, it could affect it. Is it humid? Is there UV? Is there heat? Is there whatever it may be? That's going to affect how it performs. So with that, some evaluation then within it, making sure we pick the right material to start. So are you looking at a product that's already on the market or something kind of similar? What material was being used? Is there contamination within the material? Was that particular lot of material a problem if we're talking about trying to figure out the issue? We could do FTIR to make sure the right material was being used. We could use DSE, same thing, to continue to make sure we're using the right material. Ash content testing, if it was filled. Was it supposed to be a 40% glass filled grade and it's testing at a 20? Those are things that we can do to check that and make sure it's where it's supposed to be. For the design, is the part cracking or brittle in the same place? Are we always having the same issue in the same place? It's probably a little more processing or designed based if we're having that problem. Again, did we design it with not enough venting, or is the gate too small? The first thing we would do is, in some of those cases, a quick visual test would tell us if it was a problem, or an application test. Is it a clip and that section is too thin? Well, when we go to try it in application, maybe it snaps. That would tell us the problem. But if you degrade it bad enough, you could do stuff like GPC. You could do your melt flow to see if you're seeing a molecular weight change because of it. You could do FTIR. Maybe you're getting, again, the contamination problem, or they weren't using the right material when you had designed it for ABS and they ran something else. Whatever it may be, we could use those materials or combination of them, or test, combination of them to see what might be going on. Processing, was the material not dried appropriately before we ran it? And so one of the tests, as I mentioned in my fourth bullet that I didn't really go over, would be moisture analysis testing. So is it a material that needs to be dried? Did we dry it? Because if we didn't, that's probably a big problem. We tend to find that that's one of the number one culprits, is that it's a material that needs to be dried and it was not dried appropriately. So that's a problem. But what would happen then is if I don't dry it appropriately, if I don't do the moisture test, I could turn around and do a test to figure out if I degraded it greatly because of hydrolysis. So I could do the melt flow test potentially, or the solvent viscosity test, and figure out, or GPC if we have it, but determine if we had that type of degradation coming and apparent. Was the material ran too hot? So did I degrade it because I ran it hotter than I should have? Was the mold too cold and I put in a lot of molded in stress? So again, did I freeze it too quickly before it could crystallize? That's a problem. So stuff like your moisture test, GPC, FTIR, etc. Processing, even it's kind of under the processing umbrella, but maybe there was accidental mixing of material in a dryer that shouldn't have been, or we staged it and we staged the wrong material, whatever it may be. FTIR then in that case to make sure we're using the right one, right? So there could be a few different ways to do that. And then the environment, did we oxidize it? Are you seeing degradation and oxidation because of chemical or UV exposure? We could do FTIR. Some other ones that we didn't really talk about as much, before and after color and mechanical property test retention. And so that would be more of like your UV testing. Hey, I need to withstand this level of performance and then maintain that performance afterwards. So not necessarily the test that I talked about here, but other ones that could be considered. And then for your pictures, you can see an ASA compared to an ABS. And so before and after weathering, you can see that there's an additional peak now where you're starting to see degradation of the material in the ABS because it degraded. So those new bonds that are forming from the degradation, it's apparent in the FTIR. And so that's where you can see your difference between them. And you can see that the ASA has a stable structure and does not show the same bond formation in the degradation and oxidation section of the ABS. And so these ones right here, as a little side note, is why we tend to say that if you can do it, ASA tends to be a better styrenic for outdoors. But a cool way for FTIR to show you the degradation that's occurring in ABS because of the UV weathering that it's being exposed to. All right, and then lastly, material identification. So we talked about failure analysis for the majority of it, but also on the flip side, there's material identification. So if you've got a part coming in from wherever it may be, you want to know what the material was. Maybe you have specific molders at different locations that are running something. We want to check that it's, they're using the right material. Whatever it may be, you could go through a material identification test. And so we would start with figuring out the material family, FTIR. So again, it would tell us if it's a nylon or polyethylene, ABS, whatever family it would belong to. Then we could do DSE to determine within that family what material it is. And then the last one is just an add-on, would be if it's reinforced or not. So we would do the ash test if we suspect that it's reinforced, or if we don't suspect that it's reinforced, we can do a specific gravity to check that real fast. Again, I didn't dedicate a whole slide to it, but if we know all the way down the line. We've done all the other tests. We know that it's a particular type of material. We could do the specific gravity, compare it to the expected specific gravity of that material and go, yep, it's right in line with what I expect it to be unfilled. Or if it's a little high, we can go, okay, maybe we need to do additional tests to figure out if there's something else in there that's not being shown. So what that looks like as we walk through it would be material family. So in this case, there was a study done on a nylon 6 and 6.6 and a 4.6. You wouldn't know that by the FTIR. So these are two separate FTIR scans that were done, and you can see they look very similar. That is because they are both nylon. And so looking at these spectrums, I couldn't tell you, can't really tell you which one's which. They're the same. They are nylon. And so we would have to go further than that to determine more information. So FTIR, we determined it's nylon. Then we do DSC. So now we do our little curves. Bear with me, I can see the lines are a little bit light, but the same two then materials, we then had a DSC done so we could determine what nylons those were. So in this case, you can see endothermic reaction for melt at 259 C. So again, right in that 260, 265 range for 6.6, and then a reaction at 288. So higher melt temperature of a 4.6. So now FTIR has told me it was nylon. My DSC has told me one is a 6.6 and one is a 4.6 because I was able to quantify the TM of the two materials. And then lastly, I don't have it on here because they just listed what it tested at, but a quick way to do it would be your specific gravity. So it was suspected that it was unfilled. So they did specific gravity for those two materials as well. The 6.6 came in at 1.14, which is right in line with what you'd expect it to be. And the nylon 4.6 came in at 1.18. So again, right on the nose of exactly what we would expect the specific gravities to be for those materials. So part of that being this little material ID exercise is exactly what we would have our outside labs do for you if you were to come, or we have customers that come to us and say, hey, I want to know what this material is. So those are the tests that are being done. And then now hopefully, because we went over FTIR and DSC, you have a little more familiarity with what those tests actually are telling you and kind of what it looks like when you see that data. So walking through that. And with that, that is what I had for you guys today. So thank you very much for listening in.
Thank you, Andrea, again for your comprehensive presentation. At this time, if you have any questions, please type them in the questions section or raise your hand and I will unmute your microphone. We do have Jason Merkel, our technical manager, on hand to assist with questions today. As a reminder, as you type your questions, please remember to complete the survey at the end of this webinar. Your responses will help shape future Chase the Knowledge webinars, and we always welcome your feedback. Also, be sure to check out the blog page at www.chaseplastics.com/blogs and past webinar recordings and future webinar announcements, including the Chase Plastics 101 series we have coming up at chaseplastics.com/webinars. If you would like to have a custom Chase the Knowledge topic presented to your organization, we do offer that as a service. You can reach out to Andrea or myself to get that scheduled. So let's go to questions. There was, Jason, I see 3 on here that I had already answered regarding some technical issues, but let me see if we have any hands raised.
I don't see any new questions for the time being, but for anyone left on the line, if you do have any questions, feel free to type them in the chat or raise your hand and we'll be sure to get them answered.
Also, before we dive into any questions, Andrea's last slide that she showed there actually shows our one of our one-pagers on common processing guide. So I have attached that as an attachment in the materials section. It's a great reference guide. So that's a great one to download, as well as Andrea's presentation today in the materials section.
Maybe we can have that be part of what we send out, Sherry, when we do the email.
Yeah, we'll do. Looks like we have a couple of questions popped in there, Jason.
Yep, absolutely. First question, Andrea, is what free testing does Chase provide? You want me to field that one?
Yeah, go for it.
So it's really a wide range, and I don't mean to be overly gray in my response. We don't have too much testing capabilities here in house, but what we do have is a lot of suppliers with really good relationships with Chase, whose labs we can lean on depending on what material application or the producer is. So we have quite a bit of capabilities. If it's something that falls within our supply base and isn't gonna, cost an arm and a leg, so to speak, from for them or us, then a lot of that can be done free of charge. In addition to that, we work with a handful of outside third party labs that we've partnered with to get either we'll call it negotiated, extremely low cost testing in some cases, or some that we choose to cover the fees of ourselves, depending on the business case or the selling scenario. So we'll take all kinds of questions and opportunities to test and would work on cost as a resultant of that. But for instance, some of our partnered labs, if you come to us, we're able to get negotiated rates that would be, in some cases, a fraction of what it would be if you had gone to third parties yourself. So we welcome those opportunities. We're sending parts and materials out for testing on a weekly basis. Is something we do often, and that's how we get the rates that we do. So please challenge us with any opportunities to do so, and we can give you what a cost would be if there would be any involved.
Jason, before you take the next question, we had somebody have their hand raised, and I am so sorry if I am mispronouncing your name, but Amaresh, I have unmuted you if you want to ask your question out loud.
Yeah, my question was when you have UV damage to material from long exposure, um, what kind of test does that typically show up in out of all these different tests?
Sure, yeah. So for the example given on that one, that was the FTIR test. And
Hmm.
so because there was enough damage that it was creating new bonds, new degradation bonds, if you will,
Hmm.
and that then shows as that peak on the FTIR scan. So that particular one is how they used to show that.
I see. Thank you.
Mhm.
Next question is, what would you recommend, or would you recommend, excuse me, would you recommend using MFR for determining molecular weight degradation of glass-filled thermoplastic compounds?
Filled can be difficult. We don't tend to do, and our suppliers don't tend to do MFR on filled products because you have issues with it affecting the flow and then sometimes even getting stuck in the orifice. So you don't get a very good read out of it. So it can be a difficult way to do it. So similar to your nylons and polyesters that you're not going to necessarily use melt flow for, we might not use that. It would also depend on the material itself. And in a lot of cases, for a lot of these tests, if it's material that we're selling, we also, as Jason mentioned, we worked with our suppliers. They would go through and determine the tests that they feel would be best for that. Generally speaking, though, melt flow can be difficult with filled products.
Yeah, I'd agree. I'd say, if we're looking for a general indicator, MFR might be able to give us, a rough estimate of how much degradation is happening. And typically, with molecular weight degradation, we're seeing viscosity increases of 50% or more, um, or viscosity decreases, excuse me, or in this case, MFR increases of so 50% movement. So we can compare like to like, glass versus glass. The problem is with the glass filled material, if we're comparing, virgin to something that's been processed through, say, injection molding, the fiber attrition can also kind of be a misnomer on affecting the flow rate in MFR as that glass fiber breaks down. So we defer to viscosity testing where possible with filled compounds. Andrea, next question. Which tests are particularly sensitive to or challenging for hygroscopic materials?
For that one, really the big one is going to be your MFR of the ones that I mentioned and we talked about because it is affected by the moisture. And so that's really kind of your big one of the tests that I mentioned. That's going to be most affected. And that's why we don't tend to do it for, again, the materials will pick up a lot of moisture.
Let's see. Could you start with specific gravity tests? Does that typically narrow down unfilled material well enough to establish what material category it is, if the general category is known? I guess is that specific gravity enough to indicate polymer type?
So in the case of if we knew it was a nylon and we knew it's unfilled, could we use specific gravity maybe instead of doing like a DSC to determine the type of nylon? You could. The issue comes when there's so many different types that some are close enough that we would really rather do all of those tests to determine that. But in the case of where it's something where there's not as many within that family, you could potentially use that instead.
I think the biggest problem there lies in the fact that there's quite a few polymers that are rather close. So if you get into certain polymers, say you test specific gravity, it comes in at 1.4, right? If it's unfilled, it's almost exclusively going to be an acetal, right? Now I couldn't maybe tell you if it's homopolymer versus copolymer acetal, but things like, polypropylenes and polyethylenes play in a very similar space from a specific gravity perspective. And then TPEs could fall into the same range of specific gravities as well. Some nylons and ABSs are relatively similar in the unfilled state. Not exactly, but it really depends on the accuracy of the test being done and any other potential formulation differences. Even if it's unfilled, say it has impact modifier, or say it's been alloyed with another material, can influence specific gravity. So we could get close, but I wouldn't say it's a guarantee that we'd be able to say with assurance what polymer type it would be. Next question: what equipment would I need to have to measure specific gravity in my plant?
They have special scales to be able to do that. So specific gravity is comparing it to water. So they make special scales for that. So you could purchase something like that to do it.
Let's see. How does moisture content in nylons affect melt flow rate? And should I measure moisture content before running MFR measurements for nylons?
Yes, I would for sure. We should probably, for nylon in general, know the moisture regardless, whether we're going to run MFR, which is not a great test for it, or if we're going to process it. So it's just a general disclaimer on that. It will increase your melt flow. It tends to plasticize the nylon. So if you have the exact same lot of material, if you test it one day and then you leave the box open for a couple days and it picks up a ton of moisture, your melt flow on day one versus however many days you test later, it will be a higher value. And so all within the same lot where the viscosity it should be the exact same, your MFR is going to give you a little bit conflicting data because of the moisture affecting it.
Yeah, I just posted a link. This is something I reference often when this question comes up. I put it in the generic chat and the answer to this specific question as well. Mike Seppi, who was, really a standalone guru for plastics materials and testing for a long time until his passing, has been really an advocate for why certain hygroscopic resins should not be used via MFR, and he even details some of the pitfalls of trying to dry polymers ahead of time and some of the kind of the delta you can get in response from MFR testing of nylon specifically. The same thing would apply to certain polyesters like PET or PBT as well. So I linked that for anyone to grab or save to review as needed. But even if you were to take the polymers and dry them, unless from a lot to lot perspective that they have exactly the same moisture content, which is rather hard if there's some difference in dates from which those lots were produced, it's really hard to get an apples to apples comparison. So you can draw some generalities for sure, but from an accurate scientific perspective, there's still some room for interpretation, in our opinion and in Mike's opinion, as you'll see in the article.
Mhm.
I think that might be all of the questions, unless you see any that I'm not seeing there, Jason.
Nope, that's all I see here.
Great. We'll be able to get everybody out of here on time today. So we would like to thank you all for taking the time out of your busy schedules to attend this Chase the Knowledge webinar. We hope it was informative and a great return on the investment of your time. If you have any technical questions that did not get answered today, feel free to reach out to Andrea directly. You can see her information posted on your screen. Thank you all for attending, and we hope to see you at our next Chase the Knowledge webinar.